All right, actually recording. Okay. So today we're going to talk about another type of curve fitting. So we learned about linear regression and how we did that the last couple classes, and now we're going to talk about a different type of curve fitting, interpolation. So our question today is related to this data. So in fluid mechanics, we often want to know the relationships between air density, viscosity, and temperature. And we might be given a table of information like this in the back of our fluid mechanics textbook or something like that, but we might want to know some information that's not necessarily presented in the table. So we have temperatures measured at 200, 300, 400, and 500 degrees, and then the density and the viscosity is each one of those temperatures. But what if we want to know the density at 350 degrees or the density at 450 degrees? So we need an accurate way of estimating that. So that's what interpolation kind of helps us do. And we could have done this kind of estimation using both regression and interpolation, and we'll talk about kind of which one's more appropriate in different situations. So we talked about, when we introduced regression, we kind of talked about some of these differences between regression and interpolation. So the biggest difference between regression and interpolation is that in regression we're fitting one curve to a bunch of data, and the curve doesn't necessarily go through any of the data points. We plot the data, and the curve's kind of a best fit between all those data points. Interpolation actually passes through all the data points. So the curves that we get from interpolation will go through all the data points from the data that we have. So that's the biggest difference between those two things. And that visually kind of ends up looking like this, where even with the same data, we can get considerably different curves between regression and interpolation. So why do we use regression? So there's kind of a couple reasons why we would want to do regression. We want to do that to understand how strong the relationship is between our two variables. So when we did the problem with the skydiver in the wind tunnel, we established there was a relationship between velocity and the force, and that relationship was kind of linear and had a certain kind of trend between the velocity data and the force data. We could also use it to predict something that we don't know. So with the data from the wind tunnel, if we didn't measure the force at a certain velocity, we could potentially kind of predict that or estimate that from the regression curve that we have. We can also do prediction with interpolation, and so you might be thinking, why would I pick one over the other? So typically, what we do is we look at the data and we try to understand how the data was collected and what kind of error is associated with the data. If we have data that was collected and measured with low precision, or we have reason to believe that it has some error or high error in it, then we might want to use regression, because we've already kind of gotten an estimate or a best fit to all the data, and we're not really relying on individual data points. We're kind of looking at the data all as a whole, and so we're able to use that to do prediction if we have high error in our data. If we have high confidence in our data, where we have high precision, very low error, and so we trust all the data points are good data points that we have, then we might want to use interpolation for the prediction, because the interpolation actually goes through all those data points, and so it's going to be more influenced by the particular data points that we have. So when we have high error data, we might want to use regression to do the prediction. When we have low error in our data, we might want to use interpolation to do our prediction. So that's just kind of the basic difference between these two methods in terms of what we can use them for and how we can apply them to predict things we don't know. So how can we predict the air density at those two temperatures that we don't have? Oops, I don't know why that came up in backwards order, but if they're measured accurately, what's the best method that we want to use, or what's the method that we want to use to predict air density at those two temperatures? Do we want to use regression, or do we want to use interpolation? Interpolation. So we know, or we think that they're measured accurately, so we're going to go with the interpolation, or kind of the more accurate method. So there's a bunch of different types of interpolation. We're just going to talk about one particular type of interpolation in this class, which is spline interpolation. And A spline is a piecewise polynomial, so a combination of a bunch of different polynomials. So you can have all different orders of splines. So you can have more complicated polynomials or less complicated polynomials, all the way from linear straight lines all the way up to as many as high of a degree of a polynomial as you think is appropriate. And that's what I just said. And so for any number of data points we have n, the general rule is that you can fit one less polynomial to the data than you have data points. So we're always fitting the polynomial to the data. The polynomials have to go through the data points we have, and so in order to do that, we can always fit one less curve to our data than we have data points. So that's just a general rule. So for the error density problem, we have 4 data points. So how many polynomials can we fit to our 4 data points? We had that general rule. Go back. For n number of data points, we can fit n minus 1 polynomials. So if I have 4 data points, 4 minus 1 is, 3. We even counted on our fingers, right? So 3 polynomials that we can fit to our 4 data points. If I gave you, 50 data points, we could fit 49 polynomials to our data. So what type of polynomials should we use? That's a decision that we have to make, or either I have to tell you what I want you to do. And so we can pretty much choose to fit any type of polynomial to our data. It really is up to us when we're trying to do the interpolation what type of polynomial we want to fit to the data. Higher order polynomials, so say cubic polynomials, will be more accurate than lower order polynomials like straight lines. So the higher you go, the more accurate that you get. All right, so cubic spline polynomials. We said we have 4 data points in our sample, so we can fit 3 third order or cubic polynomials to our 4 data points. And a cubic polynomial has this generic form. So we're now starting to walk through our handout that I passed out. So everybody's got this handout. I highly encourage you to follow along and fill in the blanks because it will be helpful for the in-class exercise that we'll do on Friday and for your homework. So we have our cubic polynomial, and it has this generic form. How do I know that this is a cubic polynomial? Yeah, the biggest power is a 3, so that determines that it's a cubic polynomial. If I had a quadratic or a square polynomial, then the highest exponent would be 2. If I had a linear polynomial, then I'd have the highest exponent is just the 1. So we're not going to, in this class, we're not going to deal with anything more complicated than cubic polynomials. In general, you can fit any order of polynomial, but once you get beyond 3, there's not a whole lot, a cubic polynomial, there's not a whole lot of benefit to it, unless you have some really wacky data or something like that. So generally, people deal with cubic or quadratic or linear polynomials. So we have our generic form of our polynomial. And how many unknown coefficients do we have in this equation?
We have 4.
4. So A, B, C, and D are our unknown coefficients in this polynomial. We were given X data and we're given Y data, and we want to try to figure out what those unknown polynomial or unknown coefficients are. So our unknowns are A, B, C, and D. So we have 4 of these. So if we have 3 cubic polynomials, how many unknowns are we going to have for our total system that we've got? 12. So we've got 3 curves that all have the same format. We're going to have 12 unknowns total. So our 3 polynomials are all going to have the same generic format, but I'm going to go ahead and write them out specifically so that we know kind of what we're dealing with. So we have, every one of them is going to have y is equal to ax cubed plus bx squared plus cx plus d. And then the way that we're going to differentiate between the different unknowns for the 3 different polynomials is we'll just use subscripts on all of our unknowns. So we'll have a1, b1, c1, d1, and then we'll also have, for every one of those, we'll have a different subscript. So for our second polynomial, we'll have a2x squared, or x cubed, b2x squared plus c2x plus d2. And then our third polynomial will have all the subscripts of 3. The y's and the x's don't have subscripts yet. So in kind of generic terms, this just refers to like the data we plot on our x-axis, the data we plot on our y-axis. So in this case, we're trying to predict the temperature, we're trying to predict the density at a certain temperature. So our temperature is our x data. This is our temperature. And our y data would be our density.
How do you know it's the temperature? Like, do you?
So that's the data we're given. So let me go back up. So when we asked the question, we said, how can we predict the air density at 350 degrees and 450 degrees? So our x data represents the data that we kind of know, and then the y data would be the thing we're trying to predict. So we're trying to predict density, so that would be y, at a certain temperature that we're given, the x. All right, so let's go back. So, oops, not revealed that yet. So if we have a total of 12 unknowns, right? If we look at these 3 equations, we've got 4 unknowns in each equation, so we have a total of 12 unknowns. If I'm going to solve this linear system of equations, how many equations am I going to need to solve for 12 unknowns? 12 equations to solve for the 12 unknowns, right? So we need 12 equations. So now the question is, how do we come up with these 12 equations? Where are they going to come from? And for any type of spline interpolation that you're doing, you kind of follow these same generic steps. So even if I were to ask you to do, a quadratic polynomial where the highest exponent was 2, you're still going to have to follow these same generic steps. You got to figure out how many unknowns you have, how many equations you're going to need, and then follow the same process to get the required number of equations that you have. So this is kind of a generic process that you would apply to any type of spline polynomial. So we're going to start with the first step. And these don't necessarily have to go in this order. This is just kind of the arbitrary order that I decided. So what we're going to do is we're going to kind of think about this in kind of visual terms because it helps to kind of break it up. So if I have a plot of my data, so let's say I've got my x data here, and I've got my y data, my y-axis, and I've got my 4 data points. I'm going to give each of my data points kind of labels so that we know what we're talking about. So here I'm going to have x0, y0, x1, y1, x2, y2, and then x3, y3. So now I've got a point for or kind of labels or coordinates for each of my data points. And then what we want to do is we want to fit those 3 polynomials between my 4 points that I have. So I'm going to end up with 3 different curves, one between each data point. And what those curves are these curves that kind of come from these equations that we wrote over here. So this is going to be my polynomial 1, this is going to be 2, this is going to be 3. So if I were to label them on my graph, 1, 2, 3. So now I want to fit 1 cubic polynomial per interval. So each polynomial that I have is going to be really only affected by the points that it goes through. So polynomial 1 is going to be affected by the x0, y0 point and the x1, y1 point. It doesn't so much care about any of the other data points that I have, and going on down the line like that. So the last polynomial I have is really only influenced by these last 2 points. It doesn't care about the other points that I have. So we're going to use some of this information to kind of come up with these 12 equations that we want. So our first rule about the equations is that the function values, either you can think about in terms of f of x or the y values, at the interior points that we have must be the same for the adjacent polynomials. So what does that mean? So let's break it down. So what are our interior points? Which ones are our interior points out of these 4? The 1s and the 2s, because they're the interior points here. So what that says is that the y values at the interior points, so y1 and y2, must be the same for adjacent polynomials. So that's saying that this polynomial needs to go through this point, the second polynomial needs to go through this point and that point, and the third polynomial needs to go through this point over here. So that's all that's saying. So we write those equations and we use that information. So our first 4 equations come from that kind of rule that we have. So we can write down now basically these equations, but now we start assigning subscripts to the x and y. So instead of leaving them generically like we did over here, we're going to start giving those x and y values actual names from the data we have. So we say y1 is equal to a1 x1 cubed plus b1 x1 squared plus c1 x1 plus d1. So that's the first polynomial through the x1, y1 point. We know it's the first polynomial because our subscripts for the a, b, c, and d are 1, and then it's going through the x1, y1 point because our subscripts for x and y are 1 and 1. So that's all that curve is saying. We do the same thing for all of our other interior points and our other polynomials. So now we're going to look at polynomial 2. It goes through x1, y1, and it goes through x2, y2. So we get 2 equations from that piece of information. So we write down a similar equation. We say y1 is equal to a2 now, since we're on the second polynomial, x1 cubed plus b2 x1 squared plus c2 x1 plus d2. So that's our second polynomial through the x1, y1 point. And then we do the same thing, still with the second polynomial, because we've got to go through that other point. y2 equals to a2 x1 cubed plus b2 x2, plus c2 x2 plus d2. So second polynomial through the second x2, y2 point. What do we think our last equation is going to be here? What's it going to represent? Which polynomial? 1, 2, or 3? 3 through which point? The 2, because we're still talking about the interior points. So when I write my equation, what subscript do I want to use for the y? 2. And then what subscript do I want to use for a, b, c, and d? 3, because we got my third polynomial. So now I have my third polynomial going through my x2, y2 point. So now I get 4 equations. So I've crossed 4 off the list. I still have 8 more to go. So my second rule that I have is very similar to this one. It's just that the first and last polynomials go through the endpoints that I have. So that means the first polynomial passes through the x0, y0 point, and the last polynomial passes through the x3, y3 point. So we get how many more equations with that piece of information? 2. So what are those 2 equations going to look like? Somebody tell me what to write down for my first polynomial through my first endpoint. y0, a1 x0 cubed plus b1 x0 squared plus c1 x0 plus d1. So first polynomial, a1, b1, c1, d1 through the x0, y0 point. What's my other equation I'm going to get from the endpoint rule? Which polynomial is it going to refer to? 1, 2, or 3? 3. And it's going to go through which x and y pair? x3, y3. So I write down another equation. y3 is equal to a3 x3 cubed plus b3 x3 squared plus c3 x3 plus d3. So now we get 6 equations. We're halfway there. We haven't done anything super complicated. We've just taken all the equations and said that they have to go through all the data points that we have. So we really haven't had to do anything crazy yet, right? Any questions about what we did so far? All right. So now we got to figure out, okay, we've exhausted all we can do with our generic form of our equation. We're kind of done with that. We've got to use some more information to start getting some additional equations that we have, because we still need 6 more equations. So what can we do? So we've exhausted our generic form, so let's use some more information we know about the curve. Let's use our derivative. So we're going to take the first derivative of our generic form of our polynomial, and we're going to say that it has to do a certain thing. So first off, what's the generic form for our first derivative of a cubic polynomial? So our first derivative is, like I gave it to you, so you could just read it off of the sheet, right? What do we have? dy dx equals that stuff that I wrote down there, right? So if we take a derivative of a cubic polynomial, we get a quadratic equation, so we lose a power. And so we're going to use this information now to get some stuff and get some additional equations that we're going to use in our linear system of equations. So we're going to say our first derivatives at the interior points, so that's our x1, y1, x2, y2 points, are going to be the same for adjacent polynomials. So why do we say that, and why do we not say that they're equal to something? So we don't really care what the derivative is at that point. We could be 0, it could be 1,000,000, it could be whatever it needs to be, but we want it to be the same. So why would we want the derivative to be the same, the 2 polynomials to have the same derivative at that point? What does that tell us about the curves that we have? Right, so they're smooth. So our first derivative tells us what information? What is the first derivative? The slope. So if our slopes or the first derivatives are the same, then just like Alex said, we're going to have kind of a smooth curve at those different points that we have. So we're not going to end up with some weird discontinuity or something like that. So we kind of want that information So that's a good rule to have. So we're going to take our derivatives, and we're going to calculate the derivative of each polynomial, one on either side of the two curves that we have. So what we're going to do is we're going to get our additional equations by just at first writing down kind of the generic form of the first derivative. So I say 3ax squared plus 2bx plus c is equal to another first derivative, 3ax squared plus 2bx plus c. And now I need to fill in the blanks. So the first thing I'm going to do is I'm going to look at my first interior point, my x1, y1 point. I'm going to say I want the first polynomial to have the same slope as the second polynomial at that point. So what am I going to fill in for my x subscripts here? A 1, because I'm dealing with my x1, y1 point. So I go through and I put a 1 down for all of those. Now on my left-hand side of my equation, what's going to be the subscript on my a, b, and c? 1, 2, or 3? 1, because it's going to be our first polynomial. So a1, b1, c1, referring to our first curve. And then what about on the right-hand side of here? What is the other polynomial I want to match up the slopes with? 2, because it's the other one that goes through the x1, y1 point. It doesn't make any sense to have the slope of the third polynomial be equal to the slope of the first polynomial at that point, because they don't go together. Oops, sorry. 2, that's 2. Thank you, sorry. All these subscripts floating around. So I have to have my notes, but actually if I look at them, then that would help. All right, so that gives us our 7th equation. So now we're going to get one more equation for this. So what's our other equation going to represent? Yeah, so we're going to look at polynomials 2 and 3 at our other interior point, the x2, y2 point. So we go through and we write the same type of equation, 3ax squared plus 2bx plus c is equal to 3ax plus 2x squared plus 2bx plus c. So what is my x subscript going to be in this equation? 2, because I'm going through the x2, y2 point. So I fill in all my 2's. And then on the left-hand side of the equation, what polynomial is that going to represent? 1, 2, or 3? Polynomial 2. So a2, b2, c2 for my second polynomial at that point. And on the right-hand side, what coefficient is going to be on a, b, and c? 3, because I got my third polynomial. So a3, b3, c3. So any questions about the first derivative rule? Does that make sense, everybody? So we're up to how many equations now? 8. So we still need how many more? 4. So let's do some more kind of investigation. So we've kind of exhausted what we can do with our first derivative. We don't know what the first derivative is at the endpoints, and we're not really going to make a decision about that. So let's go ahead and take our second derivative. So we want to take our second derivative. So if we take our second derivative, of the cubic polynomial, what is that going to look like? In the generic form. 6ax plus 2b. So we're going to use some information about this. And we're going to kind of use the same rule that we did with the first derivative. So we're going to say the second derivative at the interior points is going to be the same for the adjacent polynomials. So again, we don't know and we don't care what the second derivative is actually equal to, what numeric value it's equal to. It could be whatever it wants to be, but we want it to be the same on either side of that point or at that point. And so what information would that tell us about our curves? What does the second derivative give us? Let me remember. The slope of the first derivative, right? Yeah, so it's just kind of another smoothness factor. If we have second derivatives, then we're going to have kind of more continuity there at our point. So we want to set our second derivative on either side of our interior points equal to each other. So just like we did over here, we're going to set two second derivatives equal to each other. So we have 6ax plus 2b is equal to 6ax plus 2b. So if this is for my first interior point, what's going to be the subscript on the x? X's. 1. So I stick in a 1 here. And then on the left-hand side, what polynomial is that? 1, 2, or 3? 1. So my first polynomial, second derivative of my first polynomial at my first interior point. And then on the right-hand side, what polynomial is that? 2. So I stick a 2 for my A and my B. So now I get one more equation that looks almost identical. So 6ax plus 2b is equal to 6ax plus 2b. And now this is going to be through my second interior point. So what's my subscript on my x? 2. And what's going to be my, or what polynomial is this over on the left-hand side? The second derivative of second, or first, second, or third polynomial? Second. And on the right-hand side, polynomial 3. So now we're up to 6, 7, 8, 9, 10 equations. We're almost there. We only need 2 more, and then I promise the painful equation writing will stop. So what other information can we get? We're not going to go to a third derivative or anything crazy like that. Now we're going to make a decision. And this last step that we have here is really a decision that we're making. And you could make any kind of decision when you're doing spline interpolation kind of about these last couple equations. It's really up to you and kind of the way that you do spline interpolation. So in this class, the rule we're going to use is that we're going to set the second derivatives at the endpoints equal to 0. And that's just a decision that we're going to make. So what that does is it kind of makes the last 2 polynomials, so the first and the third polynomial, quadratic or second order, but we get 2 equations. So that's just kind of a trade-off that we're going to have to kind of accept, that we're not going to have cubic polynomials that are last 2 polynomials, but that's a decision we're going to have to make. It helps us solve our data that we need. So we're going to take our second derivative of our first polynomial and our second derivative of our third polynomial and set those equal to 0. And that's where we get our last 2 equations. So we say 6ax plus 2b is equal to 0. And this is going to be my first polynomial through my first endpoint. So what's going to be my subscript on my x? 1 or a 0? 0, because my endpoint is my 0. So this is talking about the second derivative of my first polynomial at this endpoint over here, my x0, y0 endpoint. What's going to be my subscript on my a and my b here? 1, 2, or 3? 1. And then I get one more equation, 6ax plus 2b, set that equal to 0. What point is that going to refer to? What x and y point? 3. And then which polynomial is that referring to? Also 3. So it's my last polynomial through my last endpoint. So now we have how many equations? 12. We said we need to solve for how many unknowns? 12. So we have enough equations to solve for our 12 unknowns, right? What type of linear system of equations is this? Is it overdetermined, underdetermined, or determinate? Say it louder. Determinate. So a determinate linear system of equations has the same number of equations as we have unknowns. So we have 12 equations, 12 unknowns. We got a determinate system of equations. So we now have our 12 equations and our 12 unknowns. How can we solve for those 12 unknowns? What are we going to have to do? MATLAB, right? That's the answer, always. So how are we going to solve for these 12 equations? How are we going to solve for our 12 unknowns in MATLAB? What are we going to have to do with these 12 equations? Make matrices out of them, right? So these are going to be big matrices, right? Our A matrix is going to have 12 rows and 12 columns. Our X vector is going to have 12 rows and 1 column. Our B vector is going to have 12 rows and 1 column. So this is going to be a big, somewhat mess, but it can be not a mess, right? If you're organized and you kind of keep track of things, it doesn't have to be so much of a mess. All right, so rather than me writing our equations and our matrices for us, we're going to spend the rest of time today and then all of class on Friday you guys working on writing your matrix form of your equations and then writing the MATLAB code to be able to solve for your unknowns. And the reason I'm asking you guys to do this, not for me to do it, is that you're going to have to do this on your homework for a different type of polynomial. So make sure that you understand how to do that. I know it seems daunting, but it's not that bad. We've got lots of practice writing linear system of equations. All right. Work. Yes, sir.